And here's our last proper lecture. Okay, so vertex cover and matchings. This is a fun one. So vertex cover you might have been exposed to, oh, we did for bipartite graphs. Now I'm going to look at it for general graphs. Okay, so you want to choose the minimum set of vertices that covers all the vertices. Okay, one second. Let me do it more slowly. So this vertex sort of covers all of the adjacent vertices as well as itself. Okay, so you want to choose a minimum set of vertices that sort of covers everything else. Okay, so what's the best you can do in this graph? Is this graph too big? It's too big. All right, what about this? I'll just point to a vertex and you tell me if I should take it or not, and we'll see what value we get. Okay, I'll start the top. I'll go row wise. How about this? Should I take this one? No? Okay. How about this one? Okay. It's true, every edge you have to take at least one. Uh, okay. Oh, we'll start right there then. You want that one? Okay. Uh, okay, well, now we're in the middle and I don't know what to choose now. Okay, do you want that one? Okay, I'm gonna go with no. How about this one? Okay. How about what's close to the middle? How about this one? Yeah. How about this one? It's gonna be easier if it was near the middle. One to its right. Do you want this one? Have to take that one? Okay. How about this one? I guess if you don't take someone, you have to take its neighbor. So maybe I should do that from now on. How about this one? I have to take this. Okay, so that means we have to take this. Okay. How about this one? Oh yeah. Okay. How about this one? You want to take this one instead? Oh, sorry, you can't see unless I draw. Yeah, okay. Okay, now back to this one. Okay. I don't know how it was faster to go from the middle. Okay, how about this on the right? Oh, how about this one? Okay, you want this one? Okay, now how about this one? No. So you have to take this one. And then how about this one? No. Okay, so what do we end up with? We end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't count. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. Oh, what did we do for this one? We didn't take it? Okay. I counted 13 circles. Anyone do better? Maybe just like looking at this and trying to modify it locally. I know that arrows make it kind of chaotic. Anyone see any way to improve it? The third one from the this one? We take this one, and then we can get rid of the one above it. And we can get rid of the one below it. Uh, this below. Okay, that does improve. Now we're down to 12. Anything else? No, this one? Why do you need this one? Uh, the edge or above or below it? You have one endpoint of every edge. Yeah. Well, so my earlier description of vertex cover was incorrect. I described dominating set. Vertex cover, we need one endpoint from every edge. But I think you guys knew this already. Just got confused. Okay. What did I get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so that's better than what I had. So that's great. Okay, good job. You win. Okay, so the question is, can you get the minimum cardinality vertex cover? Or as a decision question, is there a vertex cover of size K? That's one of the two questions we'll look at today. One thing I want to point out, uh, if we go back to our spanning tree lecture, there's this emphasis on how minimal is equal to minimum. But that's not the case here. So for this simple path, this will be a minimal solution. I can't take away anything without losing the vertex cover property. And this would be a minimum solution. Okay. I guess actually what we had before we went from 13 to 12, that was something similar. Okay. I can exaggerate the difference like this. So it's sort of an unbounded gap. Okay. The other problem we'll look at is matchings. So you've done bipartite matching. This is now just in general graphs. Okay. So I want to take as many edges as possible, but the endpoints have to be disjoint. Okay. So uh, maybe I'll let you look at it for a moment, and then we can go through and try to figure out which edges we want to take. And you can also tell me if you want to start from the densest part in the middle, or if you want to work from the top down or whatever. Okay. So where should I start? Furthest left. So this edge here, do you want to take it? Okay. Uh, maybe I'll cross out some edges that we can't take afterwards. Okay. And which one now? This one? Huh? Okay. So you want to take this one, then you can't take this or this or this or this. Which one next? Second one from this? Below that. This? Yeah. Okay. We'll take this. So you can't take this. Can't take this. You can't take this. 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 Oh, this is killing off a bunch of them. All right. Oh, and this. Long one on the top. You can't take this. You can't take this. The one below the short one. This one. This one. Even this one. This one. What the hell are you what give you right below? This one? This one? You want this one. So you are trying to take the maximum number of edges, just to be clear. Wait, seriously? So do you still want this edge that took so long to find it? Okay. Uh, it's a packing problem. You're trying to fit them in. So you can't take this. All right, which edge should I take next? The hypotenuse of the right triangle. Which of these triangles really stick out to you? There's a right triangle? Okay, I'm getting. Do you want this edge? Yeah. Okay. Can't have this edge. You can't have this edge. Uh, do you want this edge? Now let me know whenever we find your right triangle. Uh, that means you can't have this edge, and you can't have this edge. Do you want that edge? Sure. You can't have this one. You can't have this one. Can't have this one. Can't have this one. Have this one. Do you want that edge? I don't know. You have. What about this one? Okay. Where the F is this? Oh, this one? Oh, you can't take that one. Where? Oh, this one? This is not 90 deg oops. That is not 90 degrees. It, yeah, also, if it was a hypotenuse, it would be this angle. So, okay, this is a hypotenuse. Oh, this triangle. Okay. Yeah, okay. It's tough. Okay, how many edges do we get? One, two. I can't count. One, two, three, four, five, six, seven, eight, nine, 10. It's tough when everything's the exact same color. One. It all looks the same. One, two, three, four, five, six, seven, eight, nine, 10. I got 10? Yeah. Okay. So we have a gap. The maximum possible would have been 12. We got 10. Anyone do better? Remember, some of these edges were chosen to deliberately sabotage your efforts, apparently. Well, one upper bound is 12. We know we can't do better than 12. Right now we have 10. So we got a vertex cover of size. Oh, there is? Oh, do we match every pair, every vertex? Oh, we did it. We got a perfect matching. Good. Huh? Well, we still got 12 on the vertex cover side. Yeah, so now we did get the upper bound. We did get an optimal matching. We don't know if we have an optimum vertex cover. Okay, good. This would be another one. Okay, so maximum cardinalities are matching of size k. I want to make the same point as before. Maximal is not maximum. This would be maximal, where I take the two inside edges. If I take the outside edges and one in the middle, you get maximum. So they're not the same. So like simple greedy algorithms don't work. Okay, here's one more example. Does anyone see the best matching in this graph? Okay, this is a planted solution. So a perfect matching is a matching that covers all the vertices. Okay, good. All right, so we have some duality here. The edges are being impacted into vertices. The vertices are covering the edges. So that means you're going to get weak duality for free. Okay, I'll go through the proof, but it's going to be just like all the other duality proofs we've done before. Okay, so if you have a matching and some kind of vertex cover, right? You know that every edge has at least one endpoint in your vertex cover. But you also know that because your edges are disjoint, you know, those edges in the vertex cover are all different choices. Okay. So you just end up with, so you have a mapping, you assign the edges in your matching to some vertex in a vertex cover, and that assignment is injective because the endpoints of the matching are distinct. Okay. Good. All right, good. So the question is the maximum matching equal to the minimum vertex cover? We can take a poll. Uh, so in other words, will this be tight? Will it always be true that the maximum matching is equal to the minimum vertex cover, or could there be a difference? So your choices include yes, no, and not voting. Okay, so who's not voting? Okay, you're all voting. All right, who thinks that the answer is yes? So that would be like spanning trees or flows and cuts. 1, 2, 3, 4, 5. And then no. 1, 2, 3, 4, 5. Oh, I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Unbelievable. Everyone always is honest. Okay. Uh, for those who said no, why did you say no? Okay, so despite ourselves, we got an optimum matching, and then we tried hard and we got a bad vertex cover, and there was still a gap. Okay. Anyone have a more formal argument? So yes, I think would just be because that's what we've seen before. Max flow min cut, or disjoint path and min cut, spanning trees and or maximum forest and minimum spanning sets. Anyone have a no besides, I guess, what just happened to us? Yeah. Wait, 2 by 6. That's only 2 by 3. Do you really want 2 by 6? Or will this suffice? 2 by 3? Okay. So here you get a matching of what size? 3. The min vertex cover is 2. You got a vertex cover smaller than the matching? That would be very exciting. So we already know the vertex cover is at least a matching. All right. Well, Peter, who is the teaching assistant, has an idea. Okay. So this triangle, even simpler than the 3 cubes stacked on top of each other, how it was described. But you can only take one side of a triangle, but you need to take 2 corners. Okay. All right. So this is a little different than before. Okay, because they don't actually meet. Okay, so that also means that when we ask the P versus NP question for these problems, you could get different answers, okay, because the size of the vertex cover is not necessarily the size of the matching. Okay, so you have, of course, 2 choices for each problem. You either think we're going to have polynomial time algorithm is going to turn out to be hard, and also you can decide not to vote. So again, who's not voting? Okay. All right, let's start with vertex cover. Who thinks we'll get a polynomial time algorithm? No one. Who thinks it'll be hard? Okay. Is that because it was listed in the midterm as one of the MP hard problems? Okay. How about matchings? Who thinks we got a polynomial time algorithm? 1, 2, 3, 4. And who thinks it'll be MP hard? Peter, are you not voting? Okay, Peter is not voting. Okay. Um, okay, good. Let's see how it goes. All right. So minimum vertex cover is MP hard. Here's an easy reduction. Okay. Actually, forget the. Uh, imagine this is not there. Okay. All right. Consider the independent set problem. Okay. So on the left, you have some independent set problem, and you're trying to find the independent set. Okay. Look at all the vertices that are not in your independent set. I guess that's what the picture had here. Yeah, look at all those yellow vertices. What do they form? They form a vertex cover. Yep, the independent set says you can never take two vertices from the same edge. So that means that the complement will always include one vertex from each edge. Okay. Vertex cover says you have to take at least one vertex from each edge, which means you can never take, the complement can never take both. Okay. So independent sets are always complementary to vertex covers. So maximizing the independent set is the same as minimizing the vertex cover. Okay. Good. Okay. So much for that. Now for matchings. Some of you thought that there was going to be an algorithm, and some of you thought there wouldn't. So for those, the most of you who thought it was going to be hard, what was some of your thinking? Dual to a hard problem. That makes tons of sense. Okay. Any other reasons? Okay, the four of you who thought there'd be an algorithm, what was that based on? Okay, so okay, so some free upper bound is number of vertices divided by 2 or something. Okay, so this will be the floor. Any other? Makes for a better story. Yeah, you wouldn't want me to end the class on an empty hard problem. That would be a bummer. Okay, any others? Yeah. So greedy seemed effective. Vibes. Okay, I'll put that in the same category as soul. Felt it in soul. Hearts. I guess in produce spirit. Okay. Yeah. All right. What did I write? Yeah, dual problem is hard. You do know that the bipartite situation you can solve. I think that's in our favor. And finding a maximal matching is easy. I don't know if it's a strong argument, but that's something. Okay, maybe that has to do with knocking out lots of edges, but okay. Good. I guess I just want to make the point that maximal is not maximum, right? So, okay, so let's say I have a maximum matching A and a maximum matching B. Then, of course, by definition of maximum, the number of edges in your maximal is the most number of edges in your maximum. So I think the question is there a converse? Like, I don't know, is the maximal always at least square root of the maximum? Or maybe off by a factor of 100? Or at least a log? Is there any relation in the opposite direction? Or can the maximal matching be arbitrarily bad relative to maximum? Okay, so we're just going to probe at this gap. Okay, we can look at a complete graph. Then I think maximal is always equal to maximum because you can always find two unmatched. Sorry? Uh, like this one? Oh, the wheel? Maybe I can just draw it. So something like this. Okay, what's maximum is no, you can only take one. Maximal is also one. Okay, so all right. Now, so what I'm gonna do is I'm gonna try to find some relationship between these two cardinalities. And so I'm gonna take some maximal edge set and some maximum edge set. And by just throwing away the things they have in common, we can assume that they're disjoint. Okay? All right. So look at just the graph induced by their union. So throw away all the other edges that aren't under consideration. Okay. Um, all right. What's conspicuous about this graph? Or what are some observations about this graph? Is it connected? I don't think it's actually connected. Huh? Yes, yeah. So we're looking at a graph that's a union of two matchings, two disjoint matchings, and they have some characteristics. They're not necessarily connected. I don't think it's actually connected. It's like, sorry, every vert. Oh yeah, yeah. Ah, okay. So the degrees are very small. So every vertex has degree at most two. Okay, and that means that this graph can always decompose into relatively simple objects. In particular, so if something just has degree like two, then you can only kind of keep following it, right? So so that means it's just a union of disjoint paths and cycles. Okay, so it's going to be a very simple graph, kind of no decisions. So this would be one of the cycles. I'm not sure if the yellow line helps. I've grayed out the other stuff, but that would be one path that was hitting in there, and then this would be a cycle that was sitting in there. Okay? And so they're actually disconnected because the path and the cycle can't get to each other. Okay. And the path and cycles are alternating red, blue, red, blue, red, blue. Okay. Now, okay. On a cycle, the number of red edges is equal to the number of blue. So they're always tied on a cycle. But what about a path? Well, of course, or not actually, of course. So my first claim is that on a path in this union, red has to outnumber blue. It has to be greater than equal, maybe equal. But why? Yes, a maximum path. Yeah. So you take the union of the two matchings, you break it down into these maximal cycles and paths. And on a cycle, they're tied. I want to figure out how the parities compare. Now look at one of these paths. I first claimed that so red is maximum matching. And I'm claiming that there's at least as many red edges as blue. In other words, if there were more blue than red, then there would be some contradiction. Because, yeah. Well, no, not quite. Yeah, so to push out a little more. So imagine in this graph, the colors were reversed and there was more blue than red, and the first and last ones were blue. Then I can take my red matching and swap them. I can swap the red and blue and actually add an edge to my matching along this alternating path, because otherwise there's no other touching vertices, right? It's a path that's disjoint from everyone else. So if blue actually outnumbered red, then I can actually swap them. That's right. So it's actually coming from this maximum property. Okay, now the other direction. So that means blue is always losing. But I'm claiming it's not going to lose by too much. That the maximal will always be some factor greater than the maximum along this path. Yeah. Yeah, so what's the worst one? What's the worst case? Uh, oh, so first of all, this is true. Yeah, it'll be -1. But now if I wanted to figure out a multiplicative factor, okay, and what's the worst case that realizes 1/2? Just red, blue, red. You can't actually just have red by itself because blue is still maximal, so we would have just been able to eat up a red isolated edge. Okay, so 1/2. Okay, so uh, you're actually always within a factor of 2, max. You're tied on cycles, and you're only losing by 50% on the paths. Yeah, that's kind of interesting. Okay, good. So uh, now if I revisit this question of whether it's going to turn out to be NP hard, maybe that's one more thing in our favor. Maximal matching's odd. They don't give us an exact solution, but they get us pretty close. It's not bad. Okay. All right, good. Okay. All right, so now we're going to start developing an algorithm, having kind of played around with some stuff. Okay, so again, if I take two matchings and I look at their union, we're going to get these cycles and paths, and they're alternating, right? And cycles are tied, and paths, we had this thing. And the reason why there's at least as many red as blue is because you can otherwise kind of augment along these paths. Okay, so if there was actually less B edges than A edges, then I could have made B bigger by exchanging the B edges for the A edges along this path. Okay, so this is called an augmenting path. So let's say that you're working in a graph like this, okay, and you've taken those two red edges. Your goal is to get a maximum matching. And you have these free vertices. These are vertices that aren't matched, right? And of course you're thinking like, oh, well, I should be taking these three, right? And that seems to sort of match to something like, oh, let me start seeing if I can figure out how to match this guy. Well, okay, I can try taking this edge, but then I have to bump out an edge. So I might try to bump out this edge. Okay. But now I'm only 1 and 1. So now I see if I can find a new edge for this guy. I go here, right? Oh, but now I have some conflict. I have to bump out this one. Oh, can I find another one to match this one? Right? And so you'll end up sort of, when you find a path from a free vertex to a free vertex, you get an augmenting path that lets you get some kind of improvement. Okay. So a reasonable algorithm is to start at some unmatched vertex and try to walk around this graph so you're alternating between an unmatched, untaken edge, taken, untaken, taken, untaken, taken, untaken. And if this endpoint is free, now you can go through and you can swap all these and you'll increase by 1. Okay, so that's like an augmenting path. Okay, so yeah, something like this. You find this, you swap them out, your matching is a little bit bigger. Good. Now, what if there's no augmenting paths left in the graph? So a reasonable algorithm is, while there's unmatched vertices, look for an augmenting path. If you can't find one, say, oh, I'm done. But to that end, you need to know that if there's no augmenting path, then you're got a good solution. So what happens if there's no augmenting path? How do I prove that I have an optimum solution? That's true, but that's the opposite. So it's true that if you have an augmenting path, you're not maximum. But I want to show that if there's no augmenting path, you are maximum. Well, you can't do better along augmenting paths, but you don't know if there's other ways to do better. Yeah, because yeah. So if you go back to that thing from before, you're blue. You have some matching that you think is good, and you can compare yourself to maximum matching existentially, like in the analysis. If I compare it, everything will break down into cycles and path. Cycles, I'm tied with the maximum matching. And on the paths, if there's no augmenting path, then I'm tied on each path. Okay, so I break it down into cycles and path, and I'm tying on all of them. Uh, and so if there's no augmenting path in the graph, then that means in particular there's no augmenting path relative to the optimum matching. And so you win, you tied. You tied for first. Okay, good, good. So that's the kind of algorithm that we want to try to pursue. I'll start with an empty matching, and I'll repeatedly look for an augmenting path. And if I find one, I'll add it. I'll make the exchange and increase my matching. If I can't find an augmenting path, then I know I'm done. Okay, good. It's not a complete algorithm. What's left unspecified? Looking for an augmenting path. So how can we look for an augmenting path? Okay. Okay, so given some, just looking for a white space. So the idea was uh try to make like an auxiliary graph where I have all my unmatched vertices and I have also my matched vertices, relative to some matching I have. And I guess you're imagining drawing edges from one to the other. So what does this edge mean? Or what are the edges in this graph? So I should maybe clarify a little bit. We're not so much going from unmatched to matched vertices in the sense that this is unmatched, but then all of these are matched. We are sort of going from like adding an edge to removing an edge, adding an edge to removing an edge. That is kind of, yes, it's a little bit funky. All right, how about this? What do we do? What would we do for a bipartite graph? You're trying to do bipartite matching. Ford Fulkerson will work, but if we're doing it from first principles, so in a bipartite case, you have some matching, right? And you're trying to figure out if there's an augmenting path. And so like here, we can try a search. You go like here, and then here, and then here, and then here, and then here. You found like some augmenting path. The question is, how do you automate this search? Yeah, like literally randomly. I'm a little worried if you're just searching the graph, it could be exponential time. So how can I automate this search for an alternating path in a bipartite graph? Okay, so this is sort of like our homework problem. So can I make two copies of every vertex, one called red, one called blue? So I remember when I visited from a red vertex from along a red edge, or I visit along a blue edge. And then I try to get from, I think that could work. Yeah, sorry. Could you sort of for like each edge keep track of like the potential paths on it? Maybe, but is there maybe some kind of more change the graph style thing we can do? Because that might be a little bit tricky to reason. So I think this idea might work. Suppose I made two copies of every vertex, one red and one blue. So I remember which edge I came in along. Then if I'm looking for a blue, red, blue, red, blue, red, blue path, I'm trying to get from a blue free vertex to a blue free vertex. But blue can only go to red, can only go to blue, can only go to red. And I think that would be uh, kind of okay. But what happens when I revisit a vertex? So I go into it blue, and I later come back on it red. That's like I take a blue edge into a vertex and a red edge out. You walk around and you come back in on like a blue. Or no, maybe you come back in. That's okay because you've already visited a blue version of that edge, right? So the issue is you come back in on a red edge. You won't have more than one. So I think what could happen if you're not careful. So each vertex is only going to be matched to one edge, right? There's only one edge incident to it. But if you come in on blue, if you come in on blue, then you have to take red out, and perhaps later you'll come back and you'll take red this way or something, right? Well, in that auxiliary graph setup, well, with more observations could be needed because our thing would just make sure that for each vertex we just go to each colored version once, right? If we do shortest path, but it doesn't know that the red and blue belong to the same vertex and they're supposed to avoid each other. Yeah, so how do I automate this search? Try to find an augmenting path in a bipartite graph, right? Well, then you're not doing at least BFS on a particular graph anymore. So things are starting to get hacky. All right, should I stop torturing you guys? Or you want to take one more guess at it? I think you guys know this. You've kind of seen this before. How about maybe watch the direction of the lines I draw as we go, right? I go from left to right, and then I go from right to left along a red, and I go from left to right along a blue, and from right to left along a red, and then left to right along a blue. Does that give any ideas? Ah, so it looks like all the blues I'm always going to the right. All the reds I'm going to the left. Sure, maybe you could use the Floyd Warshall, but look, the directions, right? The directions let you encode the red blue because blue goes from left to right, red goes back, forwards, back, forwards, back. So we start with an undirected graph, but we can actually add directions, and that'll let us encode the parity we want. All right, so you can actually do something like this. So I direct the edges, and then I add a start. Actually, the start should probably only go to the vertices that are free, which in this case are only one. And I want to end up at a free vertex, like this. And then the directions will force us to alternate. Okay. Of course, you've basically seen this before, right? In what context? So our bipartite flow algorithm is basically doing this, right? Because the flow is going to be along the edges we've matched. And in a residual graph, it's going to be sent backwards. So if you remember originally given a bipartite graph, we direct all the edges from left to right. And that means in a residual graph, there's some edges you've taken and they're going backwards, right? So we've just kind of rediscovered Ford-Fulkerson for bipartite matching. Okay, of course, bipartite matching came before Ford-Fulkerson historically. Okay, good, good. All right, how about general graphs? So bipartite matching, we know how to get augmenting paths efficiently because of this direction trick. Can we do that here? So there's no clear left and right because it's not a bipartite graph. It's not clear how to do this. Uh-huh. Okay. All right, so the direction trick doesn't work. Okay, so can you just walk around somehow? Can you write some kind of breadth first search that's like remembering you just went on red and blue? You can to some extent. But look at this. So you go like this, and then you go down, and then you go like this. I'm going red, blue, red, blue, red, blue, just like you expect a smart algorithm to do. Red, then you come back blue, right? That never happened with a bipartite graph because of the parity. You couldn't get these things, right? But now you have this screwed up cycle. Okay? So that's right. A wild cycle appears. Yeah. Okay. That was supposed to be the words of the Game Boy song. Okay. Good. So in general, uh, we can get fooled by these odd alternating cycles. Okay. So like in this picture here, if you go through like this, uh, you might conclude there's no. Yeah. How do I put this? So imagine that. All right. Imagine this wasn't part of the graph. Okay. Now there are augmenting paths if you go this way. That would be one. If you look carefully at the colors. Okay. But if you go the wrong way, it'll never look like you're able to get out and stuff. Okay. So these odd cycles can give you some issues. Okay. So these are called blossoms. In fact, there's a whole vocabulary for this. So when something like this appears, so I have some walk and I start at some free vertex V1. Okay. And up to here, I have a path, ak minus 1 or something. Oh, no, no, no. Uh, all the way up to here, you have a path, and then you take one more edge, it becomes a cycle. And this part here, that's called the blossom, I guess. Yeah, the odd cycle is called the blossom. This part that repeats is called the base of the flower. I think sometimes this is called the stem or something. It doesn't matter. Okay, but you get the idea. All right, so okay, so what happens? So you're walking along, okay, and you get stuck. Okay, and your clever breadth first search, that first search is stuck. But we know that the give up is sort of the wrong answer because there are ways out. Okay, but what can we do algorithmically? So I found an odd cycle. Question is, what am I going to do? Okay, so how can I try to encode this in a relatively clean algorithm? It's gonna get hacky. Here's what I'm gonna do instead. I'm gonna shrink this, okay? And just turn this into a single vertex. So I'm gonna make a new kind of graph that sort of shrinks the blossom like this, okay? So I've taken that blossom and I'm treating it as just one vertex from now on, and I've reattached all those other edges to it, okay? So you have something like this. So the graph is a little smaller. In some sense, I've made some progress, okay? So doesn't this Yeah, so let's check. So then the next step is like, okay, now I'm going to try my search again, right? I come in on a red edge, and so I can leave on any blue edge. So I don't know, maybe I go like this. Okay, so I find some augmenting path in this shrunken graph. Okay, something like this. Now, of course, I'm looking for an augmenting path in the original graph, right? So when I expand it out, I have something that's sort of split up because I've expanded out that blossom. But now what? Oh, okay, so one of these two directions, in this case, going down, right? So that blue edge must sort of be in between a red and a blue in your blossom. So one direction will let you get out on the red side. Okay, so one of the two directions will work. Same with here. If I went along this augmenting path and I expanded it out and I needed to reconnect it, in this case, it looks like we can go this way. Okay, and it'll be just fine. Okay, so when we find a blossom, we're going to contract it. Okay, so that's sort of the high-level approach of the algorithm. Now, to justify this, maybe I won't do it in too much detail, but we need to argue that you're preserving the information. So it is clear that, okay, if you contract it and you find an augmenting path, you can expand it out to an augmenting path in the original graph. So in that sense, it's good. But you don't want to, like, for example, what if you contract it and you just destroyed augmenting path that used to be there, right? You don't want that. and well, okay, I guess vice versa is okay. If you find enough, we showed kind of by picture, if you find a augmenting path in the shrunken graph, then you'll get an augmenting path in the original graph by one direction or the other. So that's okay. But the other question is, if you have an augmenting path in the original graph and you shrink a blossom, will it cause any issues? So that maybe you can be a little bit careful. So it is possible that you have an augmenting path uh, that's actually coming in on so so down here we actually have an augmenting path that's coming in on two blue edges into the blossom. Okay, that means when you shrink it, it's not going to be an augmenting path anymore. So when you shrink this down to a vertex, you can't actually use that as an augmenting path. So you can actually destroy some augmenting paths in basically only this case when the two things leaving are along blue. But when that's the case, you know that at least the stem was able to get to the blossom along a red edge. So you'll get a different augmenting path, right? This will give you a different augmenting path. So even in cases where you could destroy some augmenting paths, in that case, there'll still be another augmenting path. So you won't actually preserve all augmenting path, but you will preserve the existence of an augmenting path. If there was an augmenting path in the original graph, there will still be an augmenting path in the shrunken graph, which is all you need to show it's correct. Okay. So this thing's barely going to work. Okay, good. So good. So this is this famous contraction or augmenting path algorithm due to Jack Edmonds. He also did a lot of this stuff on Metroids that some of you will be reading about. And it was an amazing algorithm, right? This was like kind of a big open problem. In fact, some people thought they already had an algorithm, but there was bugs and they hadn't noticed. They hadn't noticed this odd cycle issue. But the algorithm is you start with an empty matching, you look for an augmenting path, you either find one or you run into an odd blossom. You contract the blossom and you continue. You find an augmenting path, you just kind of expand out the graph. So you might have to expand out several times if you contract it several times. Okay. And that will terminate. Question is, how long will it take? Okay. So each iteration, you might find a blossom or an augmenting path. How long does it take for one of these graph walks that outputs either a blossom or a path? Sorry? Yeah, linear time. So you're just running like breadth first search, depth first search, whatever you want. Yeah. And then, of course, you might be worried, I keep contracting blossoms, I'm not making progress. But in fact, there's only a limited number of times you can find a blossom before you must find a path or conclude there's no paths. And so every time you're decreasing number of vertices in a graph, there's at least three shrunken down to one. Okay. And then how many paths until you get a perfect matching? Yeah, and n over two. So all in all, what's your running time? Mn squared. Okay, so that's an Mn squared algorithm for matchings, which has this incredibly clever blossom contraction step. Okay. All right, so maybe I should, yeah. Yeah. So basically, maybe I should be more clear. So you contract, 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 you find an augmenting path, expand, 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 you get an augmenting path in the original graph. Now you've increased your matching by one. Now you start over. There's no blossoms. You're starting from a clean slate, you start contracting all over again. Yeah. Why is what? Because every time you contract a blossom, the number of vertices in your graph decreases. Because there's at least three vertices in a blossom. Good. Okay, so this is a historically very significant algorithm. Actually, you guys want to guess what year this is? Why? 1973's popped up before. Do you guys remember? Bleak? No. 90s? Okay. Oh, it's the same Edmunds from Edmunds Carp. So 1973 was around Cook and Carp, right? Carp was 73, I think. Yeah. Carp's MP hard reductions. Cook was maybe 71. So you guys think this was before or after the P versus NP stuff? I guess most of you thought before around the same time? Or sorry, after around the same time? Okay. Any idea? Those who haven't volunteered to date? Will still not volunteer date then? Okay. So this is from 1963. Okay. You said 1984. So that's 9 years before Karp's reductions. That's 10 years before the C programming language, right? So we don't even really have a good model. I guess Lisp has been around because Lisp is always around, but we hardly have a model of computation that's like reasonable. Do they have what? No. When's LaTeX? Or when's Tech? Oh, this is old-fashioned typesetting. Yeah. Okay. So this is a very important paper historically. So 1963, right? I think it's like 10 years after Fulforkison. Okay. So and I've highlighted some passages here. So efficient algorithm for finding in a graph a matching of maximum cardinality. I think the key word here is efficient, right? This is like an age of practically vacuum tubes. So they were just happy to get things that worked, right? But he's talking about efficient algorithms. Some algorithms are better than others. This is important in 1963. Section 2 is a philosophical digression on the meaning of efficient algorithm, right? Section 3 discusses ideas of Bird, Norman, and Rabin, right? From Karp Rabin and Rabin is primality testing. Someone's doing primality testing. So Rabin is also one of these guys ahead of time. Berg is he's a graph theorist who studied matchings more from an existential point of view. Okay. There's an extensive combinatorial theory on the one hand to matchings in bipartite graphs, and then on the other hand to linear programming, right? So Ford Fulkerson and Hoffman. Right. There, the Koenig's theorem is generalized to a matching duality theorem for arbitrary graphs. So you see the word duality show up. Convex hull of the vertices. We didn't talk so much about LPs, but here, when he's talking about the convex hull of the vectors associated with the matchings in a graph, it has a little bit to do with how with max flow, the solution turned out to be integer, right? Other arbitrary shapes can have corners that are weird. Okay. Maximum matching of non-bipartite graphs is at present unusual among combinatorial extremum problems in that it is very tractable and yet not of the unimodular type. Okay, we didn't talk about unimodularity, but that's an important word. In a follow-up paper, he extended this to maximum weight matchings. Okay. All right, now this digression. All right. Practical purposes, computational details are vital, right? Purpose is only as attractively as I can. Efficient used to mean adequate in operational performance. In the sense that it is conceivable for maximum matching to have no efficient algorithm, right? So this is still many years before this MP hardness stuff. So he's kind of grasping at how to describe it. We might not get an algorithm, right? So he's claiming as a mathematical result the existence of a good algorithm. I mean, these all seem kind of obvious in hindsight, but this was not kind of standard language back then, right? Uh, there's an obvious finite algorithm, right? You can brute force things, but that algorithm increases in difficulty exponentially with the size of the graph. You can try everything, but it's exponentially slow. It is by no means obvious whether or not there exists an algorithm whose difficulty increases only algebraically with the size of the graph. Here, algebraic means polynomial. Okay, so it's really important to make this distinction. It's important to get a polynomial time algorithm. See, take seriously the question of the existence of a better than finite algorithm. What else is down here? Uh, we define FAN to be the least upper bound on the cost of applying algorithm A to problems of size n, right? He's trying to formulate this thing, and he says we want to get an asymptotic estimate of the running time, and that's theoretically important. Okay. For practical purposes, the difference between polynomial and exponential time is more crucial than the difference between finite and non-finite. And here's a great thing. In fact, an outstanding open question is essentially how good of an algorithm can we get for linear programming? He actually asked it for the simplex method. Okay. Right. And here he says, look, an upper bound on the order of difficulty of the matching algorithm is n to the fourth. So he didn't bother to do m for edges. He just said there's at most n squared edges. So running time is n to the fourth. We got mn squared. And yeah, he didn't even have the words BFS or DFS. He said, oh, I'm kind of growing some kind of search tree from a vertex at most n times. Okay. So yeah, this just goes on. But this was a very important thing. So we already had full focusing. We already knew how to do bipartite matchings and also weighted versions of bipartite matching, but they didn't know how to do general matchings. Yeah. And it seemed very tricky, but there was this very clever idea of contracting blossoms. And in that 9-year span between this matching algorithm and CARP 9 years later, I think there was hope that for a lot of problems, traveling salesman, vertex cover, whatever you want, that we're just one blossom contraction away from getting a very good algorithm, right? So P versus NP was absolutely devastating. I mean, there is some stuff that kept having success, like combinatorial optimization really lays out generalizations of the problems we can do. So Metroids would be one example. Yeah, but then a huge swath of this combinatorial stuff was just demolished by the P versus NP. Yeah, but you can see there's some kind of hope and excitement in this Jack Edmonds paper that, oh, okay, because this is a non-trivial algorithm, right? It's not something you'd see unless you really studied it really closely. You started drawing some pictures. And so there was some hope at that point in time. There were just a few good ideas from solving any problem of interest. But now we understand there's actually this huge divide, problems we understand and we can solve polynomial time, and problems that are all equivalently hard. Okay, we've been sort of stuck there for over 50 years. Okay, so that's our last lecture, proper lecture, and where I guess the class went. Yeah. All right, thank you. Okay.